All right. Thank you. My name is Margaret. I am a master's student in the engineering lab. We do exoskeletons, aesthetic stuff. And today I'm going to be talking about, you guessed it, exoskeletons. Specifically, it is passive silver exoskeletons more effective in the lab than what is an exoskeleton? I pulled this definition from the web. I think it's pretty good. Exoskeletons are very structures that support and assist movement or augment the capabilities of the human body. What does it actually look like? You may be familiar with exoskeletons like exobionics, as you can see right here, like as a rehabilitation device. Also, more like over here, like a research device, like kind of similar to what we do in our lab, except or this is like a version of a military exoskeleton. So this is kind of augmentation, right? We're pushing the abilities of what humans can already do. And then this is an example of like what you might see in manufacturing or kind of an industry exoskeleton, which is what we've been talking about today. So it's really anything that you can wear that makes what you do easier, or augments the movement, meaning you can do more of that movement. And some exoskeletons are even kind of less robotic than you see here, more similar to like a rubber band essentially, that or a resistance band that kind of acts as like a counter moment to whatever you're doing. So before I go on, I kind of wanted to talk about this research to industry pipeline and the issue with it. So nerds like us in our lab, like make an exoskeleton, and we'll characterize that. So we'll say, what can this exoskeleton do? A big part of that is determining like, well, maybe we can provide this much assistance and this much and this kind of movement, right? Also things like, what does its step response look like? Its battery life, kind of more boring things like that. Then we'll find an applicable use case. So we'll say, well, it's really good at doing this one movement. And maybe, you know, you at your company, you guys do a lot of this one movement. So we'll kind of characterize the exoskeleton's ability in that one movement, and then we're going to convince you to buy it. But a big gap here is that we're not really doing a lot of field testing. And so what ends up happening is we don't really know how these things work in real life, for better or for worse. So what I really liked about this paper is that while it wasn't maybe like statistically the strongest paper because of the small sample size, it really set the foundation for what evaluating these types of exoskeletons should look like. So the goal of the study was to investigate the difference in performance between two commercially available exoskeletons in kind of a real world field setting. So they were comparing the Sudex Shoulder X and the Skelex Shoulder Exoskeleton. It's a mouthful. And the big claim that both these exoskeletons make is that they're going to make overhead work at shoulder height or above shoulder height easier. And by easier, we mean reduced EMG activity, or maybe reduced heart rate, or reduced perceived exertion. It's a little broad, but these were the researchers were trying to find out. So methods. If you've read this paper, you'll realize this had a very long method section, and it was pretty thorough, even considering the sample size. So the first things they did is they identified the people that be using the exoskeletons, and then they had a 2-week adaptation period where those workers got used to what it was like to use these exoskeletons. In the world of exoskeletons, it's a pretty good adaptation period. Ideally, you'd want to see like 6 months, but 2 weeks is better than most studies. Most studies, you might get a day, maybe an afternoon. And so then these researchers came back and they replicated the lab testing that Sudex and Skelex would have done on their own. So those researchers could have gone to the website and been like, what does Sudex claim that their exoskeletons can do? Instead, they recreated those findings in what they called isolated movements. So they just put the workers in like a room like this, like, hey, hold a weight here, do this stuff. And then they captured these metrics. And these metrics were both EMG to capture muscle activation. They did that with 5 different muscle groups. ECG for heart rate, they had the Borg reported perceived exertion scale, temporal workload, which they captured with the NSATLX, a comfort scale, which is down here, which I'm pretty sure they've developed themselves, and then also an SUS, system usability scale. So they captured a ton of data. And so they did these isolated tasks, both without the exoskeleton and then with the exo and then with the second exo. Keep that in mind. And then after they did the isolated movements, they did 2, and this is just a picture of these isolated movements. So really kind of simple, not dynamic at all, but very similar to what labs use to kind of characterize their exoskeletons. So then they went and they did fieldwork analysis. So they had two different tasks, one of which was kind of they called it the ground level task. Just taking something kind of from ground level, putting it on a low rack, and then putting it at a rack that was at shoulder height. And then in the second activity, they had this like kind of forklift platform, and you're placing objects basically to the right and to the left above shoulder height. What did they find? A ton of results. This is extremely results dense. If you've ever done any sort of, I mean, just the EMG data on its own for one muscle group could have been its own paper. That's how much data you're getting when you do this. So instead of going through all the results, I just picked the highlights for all of you guys. So what did they find? So first thing is that they looked at the EMG in the upper trap, and that's because the upper trap is basically a bellwether for what's going on in the shoulder. They looked at the other muscle groups in the shoulder, but they didn't really show anything. We're just gonna talk about the upper trap here. So during those isolated movements, the exoskeletons performed as we would expect them to perform, right? So the Cedex exoskeleton at its maximum reduction was about, in the upper trap was about 46%. Skelex was about 30%. When we went to the real world scenarios, it was much, much less. So the Cedex at most only reduced about 8% in the upper trap. The Skelex exoskeleton at most 26%, but there was very little consistency between the two conditions. Both of them did much, much worse in the just shoulder height, so not forklift, which kind of means that it just shows that even if it can reduce by 26%, which is not great, it had to be in a very specific manner. And the best in-field results were seen during that forklift condition. Cedex also had a much higher reported discomfort than Skelex, and there was no clear relationship between EMG, reported exertion, and heart rate, which is something that I would honestly expect to see because heart rate's a good measure of like easy and hard, but it's a very poor measure of hard and harder. So you're not going to get a lot of refinement there from that finding. And even when they saw an increase in muscle activation, they didn't necessarily see an increase in reported exertion or increase in heart rate, decrease in heart rate, vice versa. So those were great indicators. Both exoskeletons ranked about the same in a usability scale, but the Cedex did have a reported increase in the sense of frustration. So basically the Cedex exoskeleton was worse, more uncomfortable, and harder to use. Not a great report for the Cedex exoskeleton, but also really not a great report for the Skelex shoulder exo either. So some strengths and weaknesses of this study. A strength is that they had a really robust method and statistical method analysis. The power was really weak, but I think that the analyses they chose to do is a good foundation for what they might want to do if you expand the study. I thought they did a really nice job of trying to figure out kind of all the interactions between the variables that they had going on, even though they had a very small sample size. The adaptation period for sure is an advantage. These workers got much more time to adapt than typically you see in these kind of studies. Also the fact that they chose to recreate those lab findings. Again, it would have been super easy for them to take the findings that have been published by Cedex and Skelex, but instead they found their own findings to compare to, which is really valuable specifically because they were looking at the results from person to person, right? They're able to see for this specific person in these isolated movements, as opposed to like an average that maybe Cedex or Skelex would have provided. They captured a ton of data. The amount of EMG data is insane. And all the surveys and everything else. I would never want to do the study with 50 people. Take a year, it'd be a lot of work. I liked the balance of both qualitative and quantitative data, specifically as it came to like something like discomfort, right? Like your exoskeleton could like blow it out of the water, but if nobody wants to wear it, it's useless. The scope of the claims, this paper wasn't really trying to claim anything that it wasn't, and that was great. And I think, again, it's a really great foundation for future research and attempts to kind of close this research to industry pipelines. Weaknesses, small sample size, it was only men. The EMGs were only placed on the right side of the body, which I would have liked to see it on both sides of the body, but again, a lot of data was processed there. And again, you had 4 EMGs on the shoulder and 1 on the erector spine. So I guess 1 was kind of at the midline. They also sampled their EMG pretty slow. So they sampled at 500 hertz. Typically it's sampled at about 1000 hertz, but I do think that the frequency at which they chose for their bandwidth filters was actually really appropriate for the sampling frequency. So not great, but okay. And the field work was not super representative of what the most marketable skill is for these exoskeletons. So if you look at the Sudex website, like they're gonna be showing people like bulk, like in a Ford factory, like putting up bolts for hours, right? The activities they chose weren't necessarily those specific activities, right? You're not, they claim that they are most useful where you're having a lot of overhead work and you may be static in that work. This was a little bit different. The movements were more dynamic and they weren't spending as much time straight overhead. But according to these companies, really even the work at shoulder height should have been, they should have had a bigger effect at the work that was at shoulder height. I know I talked really fast, sorry, but now I just wanted to bring it to the discussion. This is mostly just about weaknesses, changes you might want to make to the study, conclusions that you thought were justified. If anyone has anything they'd like to bring up, come on ahead. Yes.
Yeah, I have a couple questions. One, and this is just so I understand the terminology. When you say qualitative and quantitative data, what is quantitative and what's qualitative to you?
That's great. I think quantitative is obviously something you can put a number to. I think qualitative, because they're qualitative, specifically when I say that, I'm talking about the discomfort scale, because it's not validated.
Okay.
So it's more of like a metric of feedback than it is anything else.
Okay, and that's totally fine. That's just the terminology you use. So, and this is it's something I just want to highlight because this is an interdisciplinary difference, right? And that's okay. That's great. In fact, I love that you used it that way because I've heard it that way a couple of times, more than a couple of times in the journal club. And for a psychologist, and I think for some of the other, maybe for industrial hygiene, maybe for OM, I'm not sure. Qualitative refers to words, right? If I think, or other data that's not number based at all. And that includes, so that means if someone rates their discomfort with a number, that's not qualitative, that's quantitative, right? And that's just a disciplinary difference. So I'm not critiquing you or anything at all. That's great because that highlights to us when we're talking, we might use the same term to mean something else, right? So I didn't see any of their data as being qualitative in nature because qualitative for me would be like, how are you feeling? And then they would write a paragraph about how or a statement about how they're feeling, right? That to me is now qualitative because now it's words and I analyze the words using a different set of processes and so forth, right? So I just wanted to clarify that. It's just so when you talk and when you share things, just be mindful of there may be a difference within the room, right? In terms of how you understand that. And that's great. And I love that. And we should share that. So that way, when you're talking to a different group, you know to use the right term for them, right? So if I was talking to psychologists, I would not have used that same term the way that you did it. But if I'm talking to engineers, right, then I'm going to use what you said, right? So knowing that gives me education to communicate to my audience appropriately, right? And that's a skill that you can develop in journal club that translates really, really, really well into the workplace because you're talking to people from lots of different areas when you're in the workplace, right? So I'm sorry to go off on that for a second, but I think it was important to say it. Second thing was a question for you and for everyone. Why do you think, so you said earlier, they could have just done one of these things could have been a paper and they presented all the data that they had. Any guess as to why they would do that?
Yes, so I think the reason they did that, I think they were specifically trying to kind of get into this gap in the loophole of getting exo from the lab to industry. And that if you just look at one of these things, it's really easy for the company to say, well, you only looked at the EMG for the bicep. We've shown that you could do this, right?
Yeah.
Which I think is why this study did a really good job of setting up a good framework for how exoskeletons might be evaluated in the future. There's so many things you could look at and so many compounding pieces of evidence. Like one thing I didn't talk about is that a weakness of the study is that they didn't do any sort of joint kinematics. So they didn't see if the shoulder actually changed that the way it did lifting. So they didn't look at any of the abduction or adduction of the shoulder, which can be something that you could go back even after reading this paper and say, oh, well, maybe that was it, right? You didn't look at that. So I think that's the reason they wanted to present it really kind of in a full story. That would be my suspicion and based on the other papers that they have now published.
Because you mentioned that earlier, I'm like, yeah, because a lot of times I'll carve out this one piece and to do this story, then I'll carve out this other piece and do this other story, right? Yeah, you get more publications that way, but also it's really hard to make a story that fits everything. you know?
Right, and this is an extremely dense paper.
Yes, it is.
So after I read it, I was like, man, seriously, like, if this was like, if they used 10 people, I'd have been like, I'm out, that's too much. Like, you'll never, it probably really would have taken well over a year to analyze this easily. With the EMGs alone, and for anyone who's familiar with EMG testing, they synchronize all of their data as well with the heart rate, which is the reason they just sample so low, which is, it's just honestly, pass for admiration for that. That's a lot to do. Yeah, go ahead.
Seems like academic lab testing is subpar. This study showed that real world situations will be disappointing. What are the companies doing to test their products?
Yeah, so I actually used to work for, the company I used to work for was on one of the first slides. We made an exoskeleton that we did sell to the military, right? And so it's really difficult because what companies want is to be able to buy a product that they know is gonna work. What they don't want is for you to like come and like mess with their system and put things on people and like make it hard for them, right? So either the company needs to invest in like making a setup that looks like a manufacturing plant, or looks like a setup that you're gonna test it with. Or you do this lab testing and hope that it translates. I think another thing is that so many of these companies are backed by VC groups. So there's kind of an incentive to like, oh my gosh, everything's on the line, right? Let's set ourselves up to have the best results possible, right? Which is going to be the least dynamic movement, simplest kind of movement. And then speak about those results and then use those to talk to, other companies they might be pitching to sell your device to. So I think it's actually really tricky. And I think even though this wasn't a great outcome for Sudex or Skelex, really, now we have a foundation to go like, okay, well, this isn't working, right? It's not to say that the technology is bad or not applicable, but now we actually have a way to quantify it, validate it, look at it, and see what changes might need to be made, right? Like, for sure, Skelex needs to be much more comfortable to wear, right? That's an easy one to start with, so.
I had a question related to the fact that it seems like maybe these passive exoskeletons are designed for more passive movements, right? Like the example of like you're bolting this car together and you're holding your arms above your head. That's more of a passive movement, whereas they were testing more dynamic movements. And did they discuss any ways that exoskeletons could have better improvements in supporting dynamic movements? Like I know like our lab works with powered exoskeletons. So do they talk anything about the difference between passive versus dynamic movements? And
Yeah, so they didn't talk about that specifically, but one thing they did talk about, kind of field configurations were similar to what these workers do in a day-to-day. And they implied that it was difficult to maybe find a company that wanted to do this. So I think that's why they ended up choosing these activities as they did. They did mention that in future research, they hope to kind of find kind of a better fit overall. They didn't talk about that specifically, but I think that's a really interesting way to think about maybe how these activities were not best suited to get the best results for the exoskeletons.
So in here it says that between the tasks and the isolated tasks they're testing, they gave them a 3-minute break between tasks to get their muscles back. Is that a good amount of time? Because to me, it's like 3 minutes isn't long enough to fully feel better, but also it's too long to be like simulating to work tasks.
Yeah, so I think that's generally like when you're trying to figure out how much rest to give somebody, it's pretty difficult, right? Because like, who you're working with, you don't know their fitness level. I'd say 3 minutes is probably good for the tasks that they were doing, which were they were holding, I think it's a 5 kilogram weight, they held it out, and then they did this, and then they sat with it or whatever. It's probably enough time, and I don't think that it was kind of, I would have guessed if they would have looked at the reported perceived exertions and seen that like, okay, people aren't saying that this task is like an 8 or a 9, right? Like a 2 or a 3, we can like reasonably assume that 2 to 3 minutes is probably enough rest. I think it's reasonable, but it's hard to say without having been there and seen kind of what was going on.
Are like glycogen stores like 95% replenished after like 5 minutes?
I don't know
think
if
that's
that's
like-
true or false, but I believe you.
Yeah, from physiology remembering that, but I think that would be like, if that tidbit from my brain is factual, a reasonable amount of time.
Weights is gonna agree with me.
What's that?
Anyone who lifts weights is gonna agree with me. For the weight, I mean, that's nothing. You just creatine is back by then.
Yeah, I would imagine that by like the people were probably like, has it been 3 minutes yet? Like, I don't think that they were not exerted at all.
They could have also done it by heart rate.
Yes, they could have also done it by heart rate. They didn't, but you could. Again, I tend not to really like heart rate, but that's me.
So in your like from development to selling the thing pipeline, who actually ends up making these things? Is it usually just like a spin-off startup that the researchers make that do it, or do they like license it out?
So it really depends. It's kind of like what's on the market right now. So I used to work for a company called Rome Robotics, Sudex, like the person who CEO of the company I worked for is like a student, the guy who like runs Sudex now, right? So it's a very small field. Sudex is now owned by Autobach, so Autobach, which makes like all the world's like basically braces and prostheses and things like that. Like now they're the manufacturer for this exoskeleton. Where I worked, we were kind of a spin-off, right? So we were the manufacturer. It really depends, but typically where exoskeletons are in the field right now, it's gonna be a spin-off or somebody who's like left a university or has spent a lot of time in it, and then they're kind of making a startup essentially.
Okay.
Even like the Scalex, like they're from the Netherlands, I'm pretty sure they're a spin-off from a university there. It's still very tied to the academic world.
Have you worked with surface EMGs? Have you worn
Yeah.
them? Okay, can you talk a little bit about how easy they are to use and issues of
Yeah.
reproducibility?
So EMGs are, if you want to measure muscle activation, they're the easiest way to do it. That's not to say that they're maybe easy to use. In our lab, we're really lucky. We use an off-the-shelf sensor from Autobach actually. And it's relatively easy to use. You have to prep the skin. So you're like shaving the skin, they're using alcohol wipe, and you got to put it on, and then you're asking the person to flex, and you're like, okay, did I get like a good reading on that? So I would imagine it could have taken well over an hour to get all of these EMG sensors correctly placed. Once you get them correctly placed, you're pretty well off. Again, if you're going to be doing kind of muscle activation, this is the easiest way to do it, but they're not super easy to use in that where I need to put it on Kai's arm is going to be pretty different where I need to put it on my arm. So you need to have someone who really understands that and understands what those signals should look like. And each one of those EMG sensors is going to need to get the correct signaling going before you can look at it all. Did that answer your question?
It's pretty good. Yeah, what you're saying, translation is it's not easy.
Yeah, well, I'd say it's the easiest way to do it, but it's not like,
It's better than an internal electrode. or
yeah, so
something.
they have internal electrodes, which is like you put little needles in people's muscles. That sucks.
And slightest changes in use of the muscle will change your signal quite a bit.
Yes, yeah, so that is somewhat, that depends a little bit on the muscle, because every muscle's shape is different and when its activation is different. Also, what looks like high activation for me is gonna look like a different high activation for somebody else. So you really need to look at those signals as it compares to that individual in those movements. You can't really compare A to B.
You want to, ideally, once you got the surface EMG electrodes on, you don't want to move them.
Yeah, you absolutely do not wanna move
Okay.
them at all, like.
Is that what they did in the study or did they not?
Yes, so what they did in the study is I think they did all of this testing on one day, so they did not change, I'm fairly certain they did not change the EMG placement, although they didn't specifically say. So that could be a weakness.
Yeah, I thought that part of it said they were doing it on 2 days. And if
That could be-
right away is a huge problem, right?
Yes.
You're agreeing, yeah.
Although it would be pretty common, like if I was the researcher, I would have taken a Sharpie legitimately and put an X where I put the EMG.
Which is not written in here, right?
Yeah, which they didn't say,
And can you reproduce this? Do you know, I mean, it just says upper trap. That's a huge area.
yes, so what they probably did is found the strongest signal on each person's upper trap and used that as the best placement for the EMG. But EMG placement is difficult, and I think there's another reason that they chose to get all this other data is because EMG on itself is not, it's good, but it's not, it's not perfect. You're not gonna get perfect readings out of it.
Yeah, and there's a reason driving on this. If you've got controlled movement and that sort of thing, and you've got reproducible placement, and you don't move the electrodes, and you're doing it all in one day, you've got, less variability in the data.
For sure.
The more that you have those variables flying around, the more you've got problems. And once that happens, especially for subject there's a point where the tipping point, I mean, I realize we're all driven towards quantitative measures instead of qualitative, Dr. Allen. I'll use her language.
Yeah.
But at the same time, you have to be careful because when you, it may be that your board rating is actually the best measure.
Yep.
And if you look at the graphs don't clearly have a trend all in one direction, right? So,
Yeah, and that's one thing they said is that there's really not a clear trend, but.
so anyway,
So-
thank you.
Good point.
Just a follow-up question, and this is highlighting my naivety and lack of knowledge about exoskeletons and engineering in general. But how do you account for practice effects?
Oh, that's a big problem in our, not a big problem, but it's a thing that we talk about a lot. Like, so we typically talk about it as an adaptation,
Mhm.
because typically what you see is the person uses the thing more, they get better at it.
Yeah, sure.
And that's super hard to account for. So what they did here is they gave people the same amount of adaptation period. Now, is it perfect? Cause like maybe one person took a little bit longer or less. It is truly just very difficult to account for, and something that the field struggles with a little bit. So one thing I would love to see in a study like this would be something longitudinal, right?
Yeah.
Like you're looking at like 3, 6, 9 months and kind of like where this drop off is. Steve Collins out of Stanford, he suggested that I think it takes something like 13 hours, guys. Is that
Yeah, 13 hours of just
Yeah.
straight up walking.
of straight up walking in like one of their exos to fully adapt. So that's a really big burden on the researcher. Like if you
Yeah.
have this exoskeleton, you want to evaluate it.
Yeah.
I mean, so I think, yeah, it's very difficult, but we do see in our testing in the lab that people get better typically. So sometimes we see that even within like, you'll see that even within like 1 6-minute walking segment. So what you'll try to do is you'll have someone like walk for a little bit, rest, walk for a little bit, rest, walk for a little bit less, and then maybe have them come in the next week and you've like retuned your controller and you kind of see like what I think is like the maximum benefit I'm gonna get out of here, and that takes a little bit of intuition.
Yeah.
But yeah, that's a super big topic in the field on how to handle it, and I think there's not really a conclusive way.
All right, that's what I kind of was thinking, but I didn't know because I haven't
It's a
done,
great question.
haven't done anything with exoskeletons and such, so.
Had a comment from Micah online and I would echo it. Excellent job describing research that seems to have many industry-specific nuances and making the important takeaways clear to the layperson. Great job.
I think that it's time. If anyone else has any more questions or comments.
Great.
He and Kaya. put on our exoskeletons.
You got me well, you have all the background now.
All right, while we're swapping this, Dr. Heckman also asked me to talk about, I don't know if you guys picked up this article. Give me 1 second. I got the presentations. Strap in. So when Dr. Heckman sent this to me yesterday, my jaw sort of hit the floor. I would encourage you all to read it, and if you're on Zoom, I just send a link via Zoom. And basically what it is, this journalist, he's sort of a controversial journalist, that's sort of not important, I guess. But he typed his name into Google's chatbot and saw the information that it spit out. And Google's chatbot basically invented, like fabricated massive information saying that he had written articles he had never written, accusing him of saying very specific, very racist, like terrible things. So it's pretty stunning. And I think the takeaway for students and for anyone who might consider using chatbots, which I think have a lot of great purposes and all that stuff, is be super, super careful with information that you're taking away from them. And like Wikipedia has always been the joke, you know, never cite Wikipedia, that thing. But similar with chatbots, like don't, just because a chatbot is shooting information at you, don't automatically assume that it's true. So make sure that you're doing the legwork of actually getting a firsthand source and all that stuff. This, I don't know, this blew my mind when Dr. Heckman sent it to me. Anything to add?
Yeah, the Wall Street Journal editorial this morning is also fascinating. They put other stuff in there. You know, I mean, I can't remember the exact comparison, but it's like comparing Adolf Hitler with you know, something innocuous.
I think it was Elon Musk, like,
Elon
who's
Musk.
worth Elon Musk or Adolf Hitler?
Yeah,
And the chatbot said, there's no way to know, like.
yeah,
Like,
It's a
really
nuanced,
interesting stuff.
nuanced question, I think it's like.
We've had some fun citations before and it makes papers.
Oh,
that's
that's
one. Yes, they are.
Yeah,
right.
more
We-
nuanced.
We've just had incidents where it's like, oh, give me papers about ankle exoskeletons that do this, and ChatGPT will like make up citations. It's like, oh, that's exactly what I'm looking for. And then you click on like the DOI or the link or whatever, and it's a fake paper and does not exist. So
Wow.
don't just start adding papers to your citations that way.
Word of warning.
Yeah, right.
Yeah,
We need
there's
more.
also, an emerging consulting group and area around the use of AI and natural language processing systems and how to ask questions of these systems to get good information, right? So because if you just ask, like this guy did and then some of the things you guys described, it'll spit out information at you. It may or may not be real, right? And so if you query the system in a better way, then you can get better, better information. But again, why?
Good question. Pat.
So just the other week, I asked ChatGPT how to ask better questions. It told me to ask ChatGPT.
Nice.
And there was
Having
one
a
other,
crisis.
right, Paula, you said there was something about, sports articles yesterday?
Oh, there's some newspapers chains that have fired their sports journalists. And yeah, and they've hired, or not hired, but they're using ChatGPT and other technologies to write like sports articles. And so they'll like take the stats from like a high school sports game and
Yeah.
then spit out like a 200-word article. And it makes it seem like the author has never once seen a sporting event in their life. It's really sort of dystopian, like how it's describing
Yeah.
the sports. Anyway, Kai, not to take up too much more
No,
time
you're
from
good.
your presentation, but thank you for letting me go on that tangent.
Absolutely, it's important information. So yeah, Margaret queued me up super well. I'm Kai, I'm a PhD student in the same research lab as Margaret, and like she said, we work on powered exoskeletons and prosthetic devices. And today I'll be presenting on an article titled Low Profile Elastic Exosuit Reduces Back Muscle Fatigue. This paper is from 2020, and since then, they actually have developed a company called HeroWare with this exoskeleton, a more developed prototype device, but this was from one of their prototype testing kind of papers. So as far as the introduction goes, there are many occupations that require long periods of this kind of forward bending. One example they gave was surgeons who are spending hours just on surgery, leaning over an operating table, but also people working on an assembly line, or nurses, or people in dentistry. There are a ton of examples where people in occupational settings are having to just lean over in kind of this hunched position. And if you don't have good posture or whatever, you're just gonna hunch over the table, and it's gonna cause a lot of problems for you long term. But also, just as your muscles fatigue from holding that position, you undergo like undesired functional changes. And these functional changes from lumbar muscle fatigue can decrease workers' productivity, satisfaction, and safety. It can lead to injury. It can just decrease how happy they are with their job, because no one likes being sore after a day of work. And also productivity, because if you're having to stand back up and take breaks every couple of minutes and relax your muscles again, you're just not able to get as much done effectively. So the two research questions that this group sought to address was, to what degree can an elastic exosuit reduce the rate of lumbar muscle fatigue? And do changes in fatigue occur uniformly across multiple back extensors? So here's the exoskeleton that they use. It's elastic and low profile. So they call it an exosuit rather than an exoskeleton because it's more of a garment that you would wear under your clothes. It's very soft, you can wear a shirt over it, and it's like very unobtrusive is the general idea. And basically these elastic components, like Margaret said, an elastic band exoskeleton, as you lean forward, it's kind of providing upward torque towards you, kind of holding you back up to relieve some of that muscle strain. That's the idea. So it applies assisted forces in parallel with those lumbar muscles. And in this study, they provided 150 to 200 newtons of tension. So they tension those elastic bands. And that resulted in 12 to 16 newton meters of constant torque during the study. They had an ABA withdrawal study design, so they did a control, which is without the intervention, test with the intervention, and then back to another control. So they compare like the intervention to the first control, and then they compare the two controls as well to see if there were differences. And then for statistical analysis, they focused on a linear regression for the median frequency of these EMG signals. And then they also had inter-subject analysis, which was very small. For this study, they really kind of focused it as, because they had a small sample size, they wanted to see the results of each subject individually. So the last 4 pages or 3 pages of that PDF are just graphs from each individual subject. So they published all of this data just looking at each subject individually, and then had a brief section about if we combine all the subjects, what does it look like? So again, we're doing EMG and we're measuring those lumbar muscle activations. It was a 2-day testing protocol. On the first day, it was subject-specific measurement validation. I thought this was pretty interesting. They had 12 subjects come in, 7 of them were male, and their ABA withdrawal was with different weights. So during the control trials, they were holding static pose as shown here with a 16 kilogram weight, and each holding session was 90 seconds and then 15 minutes of rest in between each of the trials. The intervention test, was with a lighter weight, so they only held 11 kilograms, and then they went back to the 16 kilograms. And the idea was that they're going to use these EMG electrodes and see who can actually see a discernible difference in their EMG activation. Again, placement's really hard. There's a lot of variability. Sometimes maybe you're just not reading the right muscle. So they just use this to determine which subjects are going to make it to the day 2 protocol. And they only ended up with half of their subjects passing this day 1 protocol. So they only saw discernible differences between holding these different weights in 6 of the 12 subjects that they originally tested. And then these 6 subjects moved on to the day 2, which was to evaluate that exosuit. It was the same protocol as day 1, except they held the same weight throughout all of the trials, which was a 16 kilogram weight. And the intervention was now the exosuit. So during that B trial, they now wore the exosuit, providing that constant tension. They also had this kind of custom rig. I thought this was super cool, actually. But just to make sure that there was no variability in just the posture of how they're orienting themselves during those different tests, because the posture that you're holding can very much impact these EMG activations based on what your lumbar muscles are doing. Here are all of the EMGs that they used. They measured 6 different muscles, so 4 lumbar and 2 abdominal, and they did do them on both sides. So they actually ended up averaging the left and right sides together. There was no discernible difference between what the left side what the left side muscles were doing versus the right side muscles. So those did end up getting averaged. And then to measure that lumbar position, they wanted them to hold a 45-degree angle, and to measure they used what's called a goniometer. So here's some of the results that they had. This is data from 1 subject. This is an example of what all of that subject data looks like that you guys have in your papers. And what we're looking at is the black line is the first A1 control. The green line is with the exosuit on, and then the gray line is the second control. And what we would like to see, if you want to know if your exosuit's working, is that you would have less fatigue, meaning their slope is less steep. The steeper slope means that muscle is fatiguing faster. And so this exosuit line that's less steep than the 2 controls means that that exosuit is relieving some of the fatigue from that muscle. And then we want to see the controls back to the same place. So we want both the A1 and A2 lines to look the same. So we see that for 3 of these muscles, the exosuit helped. And then for 3 of them, well, for 2 of them, it didn't really make a difference, and the last one's kind of unclear what was happening. So we see a lot of variation about which muscles are actually being assisted by this exoskeleton, which one's fatigue. And then if we look at all 6 subjects, the green boxes mark which muscles had a decreased fatigue rate for that specific subject. So subject 1, all 6 muscles had decreased fatigue rate with using the exosuit. But subject 4, no effect from the exosuit. None of those muscles improved. What they're saying is there were 36 muscles measured, 6 muscles per subject, and There were 18 to 21, I don't know exactly how many boxes are green up there, but basically the reductions in that fatigue rate were 26 to 87%. So we have this huge range where the exosuit may or may not help this muscle, and it may help it somewhere between 26 to 87%. There's this huge range of how much that exosuit is actually helping relieve some of that muscle fatigue. We also see that a different representation of this data is where those muscles are for each subject. So most commonly reduced were these LT muscles here. And then this is their data from averaging all of those subjects together. Only 2 were statistically significant to the first control trial. So when all of that data was averaged together, we only see that the left LT and the right LT were statistically reduced with the exosuit assistance. So again, we're seeing a lot of range where maybe we're trending down, maybe the trend is the exosuit is relieving some of this fatigue, but as far as statistical significance goes, only 2 actually showed that statistical significance. Which is pretty interesting, especially with how much inter-subject variability we see just from the previous slide. Some of those differences might have been lost from averaging with subjects who may have been offloading specific muscles. Wrong way. There we go. So their discussion, these are some of the discussion points that they brought up that I thought were interesting, is that the benefits exhibited were only by like 5 of the 6 subjects. So they cut half of their study population from day 1. So they're only actually evaluating half when they get to the exosuit condition. And then once again, we're only seeing 5 of those 6 subjects actually improve. So what this would tell me is the majority of the population wouldn't actually benefit from this exosuit in the real world. In the sense that if all 12 of those people had worn the exosuit, we really don't know if only 5 of them would have still had benefits, or maybe those 6 that were cut from the first day really have no actual benefits from any sort of assistive device that might have been implemented, which means 50% of the population that might be able to benefit from this then has like absolutely, like there's no real population where this could be efficient for actually implementing in a company setting. So while they may be a viable option, there's a lot of kind of indeterminate research that needs to be done still in terms of using, maybe if they had all 12 and just had an A group and a B group on that day 2 testing, we would have seen, okay, even though maybe they're not having any difference from holding different weights, maybe we are seeing a difference from the exoskeleton assistance. Exosuit assistance had a greater improvement than reducing the weight of the held mass. So they compared the reductions from holding a lighter mass on day 1. So that 5 kilogram decrease in the mass that they're holding, and they actually saw a larger improvement from the exosuit assistance. So for those subjects that did have benefit, it was more benefit than just having to hold less mass. So that's kind of cool. There was a lot of inter-subject variability. They related this to, there were different amounts of body weight normalized assistance. This was something I thought was really strange in the study actually, was they tensioned it to 150 to 200 Newton meters for all of the subjects. So they didn't consider the fact that there's like a huge weight difference between their subjects. And so that resulted in very different assistance levels to the different people in the study. People also adapt to assistive devices at different rates. There was no training protocol in the study, and as we heard from Margaret, people can take a really long time to adapt to using any sort of assistive device, but especially in exoskeleton, there are huge training times, like 13 hours, and they just didn't have any training time with the exosuit. And so some people who had bigger reductions might have gotten used to that assistance faster than people who were not able to effectively use an exoskeleton and just weren't used to it. They did say that there were higher reductions in that mean EMG, or in that EMG fatigue rate. They did say that there were high reductions for subjects that received more exosuit assistance, which is what you would expect to see, right? If you're giving them more assistance, then they're probably going to have improved reductions. But again, if they had normalized it by body weight, we wouldn't have this question of why is there so much variability between what these 6 subjects experienced wearing the exosuit. And then their last point about probably some of this inter-subject variability is that subjects may have preferentially offloaded muscles that fatigued fastest during the A1 trial. So they have a nice plot in there showing which muscles these 6 subjects that made it were using more or fatigued the fastest during that A1 trial, and compared it to which ones had the most reduction during the B trial. And they saw that a lot of the time for subjects who had muscles that fatigued super fast, they had a huge reduction because they were just maybe able to use that one less, or able to use the exoskeleton assistance to offload that fatigue. So some of the strengths of this study I thought were readability and data analysis / presentation. I thought it was actually really straightforward to read. As far as exoskeleton studies go, this one was pretty straightforward. And then the data analysis and presentation, they have a ton of plots. Every single time they mention a different way that they interpreted the results, they have a figure to back it up, which is so helpful. But they had really great visual representations. This may be kind of hard to find the figure for the result that you're looking for if you're just looking through all the figures, but it is nice that they included all those visual representations. The custom scaffolding test setup I thought was great, because the variation in postures can really affect what that EMG activation is. And so they made sure that that was set for every single subject. They also talked a bit about the pilot testing and what they found from pilot testing. And one of those things was a confounding variable, which was the LD activation. So during this study, they actually told participants and showed them like real-time EMG data, told them to try to minimize the LD activation because people activated their LD muscles very differently. So some people, as they fatigued more, would activate those ones more, or some people activated them a lot at the beginning and then it decreased towards the end. And so that was a very big confounding variable during pilot tests, apparently. They didn't show data from it, but that's what they said. So they asked participants to try to minimize that activation. That way they could actually measure that lumbar activation more clearly. It was a withdrawal study design, and that strengthens the inference that the observed change was caused by the intervention. So because they went back and did a second control, you can actually really compare, okay, the difference was because of the exoskeleton, not because they were holding the body a different way, or because they felt better after 15 minutes of rest, or whatever it is. And then finally, the variability in the MBF data points were consistent between trials. So on the plot for that one subject where you saw all 6 muscles in the 3 lines, the variability of the data points around each of those lines was consistent for all 3 trials. Which is interesting because a lot of the time you see increased variability when you see an exoskeleton. Body kind of doesn't know what to do at first, so you get a lot of variability. So it's nice that the variability was consistent because it means that people might have been reacting pretty well to the exoskeleton. Now, some weaknesses that I identified were that only 6 subjects were evaluated. It's a small sample size. It's actually not that bad in terms of like exoskeletons, especially like a study that was published in 2020. It's hard to find people who will come in and wear an exoskeleton. My guess would potentially be these were grad students in the lab, which means maybe they did have an adaptation period because they've been wearing the device in lab because they built the device, whatever it is. But only 6 subjects is not bad. I just think it was weird that they cut half their population from day 1 to day 2. To me, it says, okay, well, we're not going to see anything from these 6 anyway, so we're just going to remove them from the study and try to justify it. So yeah, that leads me to the question, would exosuits be viable for the other 6 subjects that we cut? And then they also had non-weight normalized assistance with a 44-pound weight difference between the lightest and heaviest subjects. So that means I'm getting the same amount of assistance as someone who is 44 pounds heavier than me or lighter than me. And that led to this is the range of body normalized assistance. It was 2 newton meters per kilogram to 3 newton meters per kilogram. I'm not sure that means a lot to everyone in the room, but those of us who work with exoskeletons, that's a huge difference. I think you can just see even like it's a 50% difference. So that range makes it really hard to interpret some of the results of single subject data, just in terms of was this the person who's receiving a ton of assistance or the person who's receiving the lightest amount of assistance. And subject 4, who happened to be the subject who had no muscle change in their reductions, they were the one who received the least amount of assistance. So there's some discrepancy in if everyone received the same amount of assistance, we'd have a much better idea of what this exosuit might actually be useful for during some of these tasks. And then because it was a single subject study design, it limits the conclusions that can be drawn from this data because they're trying to say each subject's individual and we don't want to combine all their data and see what it looks like. We just want to look at 6 different subjects separately. And it kind of weakens the fact of you're basically saying you know that this will not work for everyone. And yeah, there's a lot of work to be done and they know that, but it really weakens the study. There's also large variability in that subject response, which muscles decrease, which muscles increased. That's super variable. And then they also didn't test this in any lab settings, which, or any occupational settings. It was all in a lab setting, which if you're thinking about like forward bending, kind of makes sense, but also you're in a scaffolding structure, which I thought was great in terms of you wanting to standardize this measure of EMG, but you're not actually going to be in a scaffolded structure if you're a surgeon leaning over an operating table. So that's my interpretation of this paper, and here's some discussion questions that I have for all of us.
I have one, which is, I know you talked a lot about how they cut 6 people from the study.
Yeah.
Maybe this is more of a comment than a question, but do you think it would have been better if they had, instead of standardizing the weight that people were holding, giving people weight until they saw it, like increasing weight until they saw a change in that EMG pattern, and then kind of doing some sort of fatigue mapping for each person, considering they didn't even combine the results?
Yeah.
It feels like kind of like an obvious, like, well, we could have done that.
I think it's a really interesting comment, especially in terms of they were holding a constant weight on the day 2 testing as well. And they just gave everyone that same weight, whereas holding 16 kilograms for Jesse might be easy, and for me, it might be really hard. And so already that variability is
Right.
huge. And so by saying, okay, well, we're going to start off with like 5 kilograms and then 10 and see where that difference is, that might have been a much better way to do it and be able to include all 12 participants as well.
So this is a question for you, but also for everybody else. What are the statistical reasons why they did not find a significant difference? Well, I think most of you have been in my biostats class, so you know the answers to this question, so. You've already been talking about it.
Low
Whether you
power,
realize it or not. What's that?
low power.
Okay, first off, low power. They hacked off half their sample, making their power even less, for one thing. And then you talked about how that some are getting assist, some are not. So some of the operationalizations are making it less likely, creating huge variability, which larger variances, larger standard deviations means there's gonna be the whiskers on that box and whisker plot are gonna overlap. And when
That
they
makes
overlap, they aren't gonna be statistically significantly different. And so when I looked at that, I was like, wow, that's a huge difference. But I'm like, oh, wait, their whiskers are overlapping. So it's not gonna ever show statistical significance. But practically speaking, there was a huge difference,
Right.
right? And so that's when, with low sample sizes, your typical statistical analyses aren't gonna work unless you consider these other things, right? And so I think what may have happened, since you said that they started their own company and like that, is they realized they had a huge difference here.
Right.
They published it this way, and which kind of minimized so, hey, guys, we found nothing. We see nothing here.
Don't
And
steal our design.
don't steal our design, because it didn't work, you know? When in reality, everything you were saying was like, okay, if we did these things, it would be we would tease apart that difference.
Mhm.
And if they had a larger sample size, they would tease apart that difference further. And if they had greater controls and less variability, yeah, all of that would make it so that way, wow, we have a big difference here
Right.
and this is meaningful and we should go start a company. So.
I was also gonna say, I'm not super familiar with how the HeroWare exosuit works in terms of adapting the assistance given,
Right.
but I could see that this could be maybe a good application in a field where, say, like it's predominantly dominated by large men. Even though your results are kind of like a mixed bag of like, is it effective, is it not effective? I still think it does show like even being effective for some people is valuable.
I like the perspective of publishing this with the idea we're gonna go start a company with it,
Yeah.
and we wanna show these results, but we don't wanna make them sound too good.
Yeah.
Cause it feels like that's what they did,
It does, it really does, because there were some simple things they could have done to make
which I
it.
think they knew about too.
Oh,
Like, I
yeah.
think it was super obvious to this group, like.
You gotta push a paper out.
Kurt, I have a question for you, because you used the example earlier and you showed the picture of the surgeons and something. Is surgery even on the radar of using exoskeletons to support them as they do their work, or is that just
Research
bizarre?
side, yes, in the field, no.
Okay.
People have done things the same way for 100 years, why change now? You did a very good job, by the way, both of you. Complex stuff and boiling it down to my level, so that was really.
It's not as hard as you think.
Yeah. So how do you think that they kept the EMGs consistent from one day to another? Because we're again dealing with the.
Again, they didn't mention it. They didn't, I think that their comparison, like they didn't compare the data between the 2 days, they just used day 1 to cut people basically. So from day 2, they very well could have placed the EMGs entirely new because they were just comparing like day 2 trials to each other. So I think it's less of a potentially problem area here.
So they didn't describe their subjects at all. You presumed it's grad students, that's a reasonable assumption.
Yeah,
But might there be might there be differences in demographics, body, habitus and so forth between the two groups, the included group and the excluded group?
I think there's a good chance. Again, they didn't really say. We know that males and females were in both groups, and that's about all we know. So at least there were females involved. That's great. But in terms of like maybe people who are really small, it doesn't work well, or people who are really big, it doesn't work well. We don't have that information, and it would have actually been super useful to help interpret some of these results.
How do you think they would have differed in those simple variables, age, sex, BMI,
Oh, that's a great question. I have a feeling that people who are potentially stronger, not necessarily larger, but maybe with more mass would have a harder time seeing that reduction in between those muscles. I think maybe people who, I don't want to necessarily say age, I wish I had that age statistics. Maybe people who are younger, maybe less training, less still growing, I don't know, but people who are a little younger maybe would have an easier time also seeing those reductions. But they also might have a lot more variability between that day-to-day EMG activation.
What I'm getting at here is that gets into the generalizability of the data, which we
Yeah.
have an extremely difficult time.
I think it's really difficult for this paper. I think that this is a great paper for the time period for being 2020, and like occupational exoskeletons are still super new. It's still a super new field, and I think that this was a group who's kind of ahead of the game for the time period that they did publish this in. And I think, like, again, we talk about a lot of ways we can make this study much better. And I think that that's a really great example of like club sport, because if I want to go and do an occupational exoskeleton study, I have a much better idea of ways to do a good job about it now.
And ways to mask having done a good job.
Yeah.
So you could go start a company and be able to say, oh, we scientifically published it, see? And yet, yeah, sorry.
With the way that they say that like the people with the most resistance obviously had the most effect. I would have loved to see a dose response like per person, like how much does that change affect each person, and see what that dose response curve looks like. Cause like maybe for the small person, it would have done a ton,
Yeah.
or maybe there's a max where like this no longer helps, it actually makes it harder because now it's trying to pull you back up and you're pushing
And you're
down.
fighting it.
Yeah.
I think having had experience with exoskeletons, tuning is one of the hardest parts of it because everyone responds differently. And I especially I work with stroke patients, and that's a whole other ballgame in terms of variability. But there's definitely a plateau period. And there's also like that adaptation period. As people have worn it more and are more used to it, you can give them more work. You can give them more assistance because they're more used to it and can deal with it. But otherwise, if you start them off too strong, they just fight it the entire time.
Do you think, just trying to understand this field a little better, it's interesting.
Yeah.
I've never heard, this thing about like masking the results so you can start your company, and then, do you think that they would, now that they have it, they would be motivated to study it further, create more robust scientific, evidence to support it?
I would hope so.
They actually just released, so Hero Aware, which is the spinoff, they actually just released one of their biggest white papers like 2 weeks ago.
They did just release like a really cool white paper, but like between like this paper and that paper, there's basically nothing. So I think that's one of the really hard things about this field too, is like you want to be the first in the door, And it makes it super competitive and you come up with this dynamic between how much do I share, how much do I publish, how much do I tell people? Because I don't want them to catch up or beat me here. And I think that it's one of the really interesting dramatic parts about being in exoskeletons right now. But I think like the masking the results made a lot of sense for where this paper was at now, and hopefully they'll start releasing more of this data now that they're established.
I'm sure they're doing internal development
Mhm.
studies, right? And the release of the white paper is kind of their way of saying, hey, we figured it out, but not sharing enough to allow someone to just copy their design and so forth. So, yeah, I don't know, I don't know if this is what they're doing, but it sure smells like it.
Well, and the fact that they have a company now.
Yeah, I mean, it just, yeah.
And the
Was that
really
one?
obvious sort of, you know, what we would call demographic data about, you know, age, sex, body mass, and, you know, all that. You think that was intentional obfuscation to avoid them limiting their own ability to market it to different populations?
Well, yeah, I'm kind of feeling like it
Maybe.
now,
Maybe.
through this discussion. But also like it's a super common thing, like, it's one of those things that's obvious, of why wouldn't you include it? And maybe that's why.
Maybe they didn't want to say that it was their grad students though.
And yeah, but like, I can put it in and be like, oh, I'm gonna have a postdoc wear it too, and then like that drags like the age curve up. There are ways to get around it.
I'm sorry, I was saving them up. But one more question.
Yeah.
Do you feel like in labs like this, in which I have no experience, they kind of already know what results they're gonna get? And they wait till, you know, because they've been dinking around with it and stuff, and they wait till they're pretty confident in the results, and then they're like, okay, let's press the go button on the study, and, you know, that sort of thing.
I think it depends a lot. I think the first thing to note is these studies can take a really long time. Like my first PhD project, I'm a Pruyn PhD, but started as an undergrad in the lab. I've been working on this project since my junior year. It's taken a really long time to collect all the data, to find participants, to get the device working the way I want it to, right? Even then, I know, okay, this is what I'm probably going to see. But then you also get surprised by a lot of things, like, I think maybe you know like your key outcome, like, oh, I want to show that EMG activation improved. But if they had gone a level deeper and said, oh, well, maybe why, and asked more deeper questions like, what if we do throw in kinematics and can kind of evaluate, hey, if you can improve this specific thing, if you can improve hip angle compared to like your thigh angle compared to whatever, that will actually make it easier to hold this position longer. I think that that's kind of a much more interesting question than just, is this a feasible device? I think there are much deeper studies that can be done. And if you are answering those research questions, you don't know as much of what you're going to find, and it also takes a lot longer than maybe this study would have.
And one more comment, I think you're also getting at individual researcher motivation, right?
Mhm.
Some are gonna be like, hey, let's start a company, some are gonna be kind of geared towards that, or let's get a patent or whatever. So there's gonna be some that are gonna be masking or not, either masking their results or just not sharing them as quickly, right? And then there's others who are very transparent. They're all about getting their new thing into the best journal possible to be the top mind and idea person in the area as a researcher, right? And you have everything in between, right? So I think depending on the motivation of the researcher, you'll see very, very different approaches to how they do their lab and how they proceed with their publishing.
It's all super strategic.
Yeah. So.
Okay, well, thank you.
Thank you.